All right, we're continuing in chapter 9. In chapter 9, we're going to talk about spring energy and power. And so these are all parts of energy and work as we were relating to from the last time. So we're continuing on. The difference with a spring is if you have a spring and you stretch the spring out. So we have in our spring here, we have what we call its relaxed position. And a spring works because the forces between the molecules, the bonds that are holding the molecules together, want to maintain their spacing or the position. And if you stretch the spring, if you pull it out, you apply a force outward, the spring wants to return to its normal position. It also works the other way. If you push or compress the spring, it also wants to spring back out to its what we call relaxed position. And so the force on a spring is always opposite to the motion that you put on it. Or we write this as what we call Hooke's law, which says that the force from a spring, I'm going to put it sub S here, is always minus kx. The negative is telling us direction. So if I stretch it out and I make positive this way and I go in a positive x direction, I pull the spring apart, then the spring is going to want to apply a force backwards, back to the way it was. And if I compress the spring, if I go in a negative x direction, then the negative cancels out and you get a positive force. So it's always going to be in the opposite direction of the way you do that, which in the positive opposite direction of the way you move the spring. If you compress it, it wants to extend it. If you extend it, it wants to compress it. Now, the reason we haven't used spring forces before is you notice that the force is now a function of distance. In everything we've done up until now, we've always assumed constant forces, constant accelerations. And so it becomes tricky when you're dealing with springs because as you pull the spring out, the force is little and it gets harder and harder and harder. The more you pull, the harder it gets to pull it more. And so it's easier to deal with forces, with springs if you treat them as energy instead of dealing with forces, because technically you'd have to do it as using calculus because the force is a function of x, and so it's continuously changing the further you move it. But we can do it as spring energy. And spring energy, or we usually do this as potential energy. It's potential energy of a spring. Because it's always potential energy, just like gravitational potential. When you have a string expanded, then you have potential to come back together again. This is 1/2 kx squared. So what's this k showing up in here? This is what's called the spring constant. And the spring constant has to do with, that's the k. The spring constant has to do with what the material is. If it's metal, how thick it is, how hard it is to pull the spring or compress the spring. The bigger the spring constant, the more force you have to apply to move it a certain distance. It's like springs on a vehicle that hold your suspension are very strong springs. And it takes hundreds of pounds of force to make anything move. Or you can have very tiny springs that expand very easy. So the spring constant wraps that up in there. And the spring constant does have units. The spring constant has units of newtons per meter. So then when you multiply it by meters, it ends up with newtons. It ends up with the force. Well, that same spring constant is the spring constant down here. Okay? Notice that x down here is squared, so it doesn't really matter whether you're going to compress it or extend it, whether it's a negative or a positive value, because once you square it, it's going to end up being positive anyway, and spring energy is always going to be a positive value. So that's how we use it, and we can use this in our energy equations. All right? Now, what we also are getting to is what we call the conservation of energy. The conservation of energy just says that the initial energy has to equal the final energy if there are no external forces. All right. Now, if there is an external force, then it applies work. And so if there's a force, so this is always true, if there are no external forces. If there is an external force, then we can still do conservation energy, but we have to use that force and figure out how much work that force does. So then it's the energy initial plus the net work done is equal to the energy final. And remember, the net work could be positive or negative depending on how the force goes with respect to the motion. And so you could start with a certain amount of energy and the work takes away from the energy and you end up with less energy, or vice versa, you could add to it and get more of it. So if there are external forces, you have to do it like this. All right, let's go back to friction. Remember, we talked about friction. I actually did a problem that had friction in it before, but I didn't really explain it. We're going to treat friction as thermal energy, because that's really what friction is when you rub things together, the friction actually creates heat. So you're taking the energy, the work done by the force moving it back and forth, and you're turning it into heat. And so the thermal friction is just going to be equal to the kinetic friction over the distance that it moves. Essentially, this is going to be, remember, work is equal to FD cosine theta, right? Well, the force is just the force of friction. D is the distance. Now, the cosine of theta goes away because it always opposes the motion, so it does negative work. Okay? Stay with me here. Energy thermal is always going to be positive. It's always going to be a positive value. Okay? And remember, energy thermal, we can rewrite this as mu sub k times the normal force times the distance it travels. That will always work. Okay? But the energy thermal always goes on the energy final side of the equation. So if we're doing problems where we conserve energy, we're going to put our energies either on the initial side, as the energy you start with, or on the final side. You never start with energy of friction, because friction can never give you energy. It just takes it away. So some of your final energy has to be taken up in friction. So this always goes on the final side. If you remember that, you won't have a problem. And if you do this right, then everything you put in, all the energy you put in, will always be positive. You just got to make sure you put them on the proper side of the equation. Makes it a whole lot easier. All right, let's talk about power. What is power? Power is P, which is just work done over time. Okay, remember, work is in joules, so this has units of joules per second. But we call a joule per second, this is a joule per second. We call a joule per second a watt. So we measure power in terms of watts. Okay, and you're familiar with that if you've ever paid an energy bill. You pay for how much electricity, you usually pay in what they call kilowatt hours, or thousands of watts used per hour. Now remember, power is work over time, okay? But power can also be represented as energy over time, because remember, work and energy are equivalent. And when you do energy over time, it's still the same units, you still get watts. Okay? So either one of these works. It depends on the situation. If you're applying a force over a distance, then you're going to put it in as work. If you're applying energy like gravity or something in here, or kinetic energy, you put that energy in here. Either way, you're going to get the amount of power done. Okay? Now also, remember that work is equal to, let me rewrite this. So I'll start up here. This is work over time, but we can write FD cosine theta over time instead of work. Okay? But we can rewrite this as saying, oh, this is force, as long as the force is constant over that, d over t times cosine theta. But distance over time is just velocity. So power can also be written as the force times the velocity times the cosine of theta, as long as the force, this is a constant force over a constant velocity, then it works. So be careful. This only works on those occasions. So these are the equations you need to know for dealing with power. And remember that power is in watt, energy is in joules. Okay? All right. That is what we need to know to finish Chapter 9. These are the problems that we're going to do to practice so we know that how to do problems in Chapter 9. So we're going to do 29, 38, 40, 56, and 66. And I'm going to put in more videos to show you how to do these, but again, do them yourself and then just use my videos to check to make sure you got the right answers. Or if you get stuck, then you can see how I do it. But it doesn't do you any good to just go watch me do it, because then when I'm not there, you won't be able to do it on your own. All right, let's continue with Chapter 9 then. Start working on these problems.